Hello class, this is Miss Jacoy. So we're working more on free body diagrams, also called forced body diagrams. You'll see both. Remember, I'm going to abbreviate it with FBD. So I want to go over how to draw them and how to use them using Newton's second law. So how are we going to actually use these free body diagrams to solve, what is the actual force on the object and therefore what is its acceleration? Remember, Newton's second is F equals ma. But remember, we're going to start making that a little more complicated, talking about not just a force, but adding all of the forces on one object. So when you're drawing free body diagrams, we only care about one object or system. What I mean is that whatever's happening in the environment, we just focus on what is happening to one thing and how are other things affecting it, but we don't consider them as anything else. And then any object, we've already talked about it, but any object or system, we use a dot. Simulate person, car, plane, bird, doesn't matter, it's a dot. So from this dot, you want to draw the forces that are affecting it, and we represent our forces, or F is force, with arrows. So all the different forces acting on it are represented as arrows coming from the center. So let's say it has some sort of rightward force, some down force, and some force pulling it to the side. Then we have to label every single force, right? We do this, right? Force is the capital F, so they'll all be labeled with force. Then you need to go back and label what kind of force in the subscript. So I'm just using generic letters now. So this is the kind of force. Alright, now I'm going to do an easy example. So we've already talked about this, but the example would be a book on a table. So we can draw our book on the table, but really what we want is not an actual drawing of our book on a table. Yes, that's a book on the table. But remember, we're going to represent it with just a dot. From here, you want to list what forces are on it. So it's a book on a table, right? It's on Earth. So we know that we do have the force of gravity. And it's not falling. So remember that our surface force that's perpendicular is called our normal force. So that is also acting on it, so it's not falling. So then to go and represent this, we need two arrows. One for gravity, so you label it force, and G for our gravity. Then an arrow going up for our normal force, which is force N. Alright, and then notice these are roughly equal lines because, hey, if we had unequal, if we just had, say, the force of gravity, that means it's accelerating downward. If we have none of that, that means all of our forces must be equal. So I want you to try one, which would be, so we have a chain with some keys. I do want the keys to be your system, so what forces are acting on this keys? Go ahead, pause the video and try it. Alright, now that you've taken a moment to look at this, hopefully you realize that, hey, it's still on Earth, so there is still a force of gravity, which is, remember, a downward force for our keys. Alright, but why aren't the keys falling? Well, right, there's the chain. But let's think about this. How much chain is there? Is it one string? Or you actually have to include two of them. Each chain has its own force. And that would be an upwards force. So to draw this, right, we draw our gravity, which should be Fg, and then we'll have to draw unchain and another. So these both would be forces from our chain. But remember, we call this tension. So it would be the force of tension. So that kind of looks like an E. I'm going to redo that. So it'd be the force of tension between, for our chain being pulled up by its chain, for our keys being pulled up by its chain, and gravity pulling it down. So we've been learning about how when we do Newton's law, F equals ma, we can't just leave it with F equals ma. We have to do it in a specific direction. So we have to have both the sum and this is force in the x direction. Remember that is in newtons. Then we have mass, which has no direction. It's a scalar, which is in kilograms. Then we have acceleration in meters per second squared, and this is only in the x direction. So we can do the same thing for y, only in the y direction. The same idea, but for every force you have to break it up into its x and y components. So we'll learn more about how to do that with geometry. I know, exciting. But let's first talk about a more simple one, how to break it down. Alright, so we have some object being pulled by a force A and a force B, but we can't, it's hard to tell right now in which direction it should probably be going. So what we need to do is break this term, the FB term, into different parts. So the way to do that is you can see, oh look, this is how far up it's gone. And then this is how far left it's gone. So we now see that, hey, these actually look pretty equal, these two terms. So these are going to mostly cancel out. Maybe it'll go a little this way. So our net would end up being like this and this. So from here you can be like, okay, well, it's going to go up in this direction, a little bit up, mostly up and a little bit to the right. So we're going to start working on how to break down those into just the f and x, and then after we break it down, we can do some math with them. So here's our example problem. We have some object, doesn't matter, it's being acted on by forces in all directions, but notice they are unequal, so you have to solve each piece separately. So we know the mass of this object to be 3 kilograms. Remember, F equals ma still applies, Newton second. So we have to find the acceleration in both the x and the acceleration in the y. They must be done separately. So let's start with the x. We have the sum for x is equal to the m times RAX. So for the sum of this, you're essentially doing the right minus the left, because left, right, we always call left to be negative, so you will subtract that term, the left term. And then if we look at sigma Fy, it's the same idea where it's the mass times acceleration in the y, and remember we always like to call up positive, so it's up minus down, because we called down negative and we're adding them, but really since down is negative, we are subtracting them. And then as far as solving goes, you just have to plug in your numbers. So on our f of x, we have 5n and 6n, or newtons. So it's our right is the 5 term, so it'd be 5 newtons minus the left term, which is 6 newtons, gives you negative 1 newton. Then to solve the y term, all you have to do is put in our y, which is 10, n is the up, minus the down, which is 2 newtons, so it'll give you 8 newtons. And then you just plug those back into your, what you know your y and your m to be. So 8 newtons is equal to 3, your mass up here, times the acceleration in the y direction. Divide both sides by 3, and you get 2.67 meters per second squared. Do the same thing, and this is for, remember, acceleration in the y direction. Then we go back and do the same thing for x. We knew it was a -1 newton is equal to 3 kilograms times our acceleration in the x direction. Divide by 3 kilograms on both sides, and you get ax to be equal to -0.33. Alright, now I want you to try one on your own, so I want you to try it. Same thing we did, finding the sum of all the f in the x direction and the sum of all the f in the y direction, and find the acceleration for each direction. So pause the video, try to do that on your own. So let's do x first. So sigma fx is equal to m times a, oops, almost wrote y, and x. So it's the, remember, it's the right minus the left. So we have, our right is 1 newton minus the left is 2 newtons. This is equal to our 5 kilogram mass times our acceleration in the x direction. Subtract, you get -1 n is equal to 5 kilograms times ax. Divide by 5 on both sides, and you'll get -0.2 meters per second squared is equal to acceleration in the x direction. Alright, then moving on to Fy, or sigma Fy, it's again mass times the acceleration in the y direction, and it's up minus down. So note, we have 2 ups here, so you will add those. So it'll be 3n plus 3, and hopefully you can add 3 plus 3 is 6. And then you will subtract whatever is on the downside. And that's equal to 5 kilograms times your AY. So 3 plus 3 gives you 6n minus 6n. So this term adds up to 6n minus 6n will give you 0. So 5 kilograms AY equals 0. That means that AY has to be 0. If that anything, the only way to get 5 to equal 0 is multiply by 0. So you are not accelerating at all in the y direction or the up and down direction. Alright, I hope this video has been helpful in helping you understand force body diagrams better. We will continue this on Monday.